One of the awesome things in 5.5 that's now been introduced are raycasting. Now, effectively, raycasts are just line traces that are now able to be done in PCG, and they're not new in Unreal in general, but they are new within PCG. Using raycasts, I can take my spotlight and effectively have it create and spawn points wherever I'd like. In fact, it actually follows the angle and everything. If I angle it this way, you can see it is now following the angle and cutting out where it needs to. And if I place a wall nearby, it'll go ahead and start spawning up on the wall, following the contour of the shape. Now, it's not 100% perfect, but this uses a lot of the new functionality in 5.5 that hopefully will get your mind thinking about the possibilities and the things you can now do thanks to raycast and a few other features that I'll be showing you in this video. So let's get right into it. To get started with PCG, first go to Edit, Plugins, search PCG, and turn on Procedural Content Generation Framework, PCG, turn it on, press yes to the message, and just go ahead and restart your engine. Once you have restarted, we can go ahead and get started with PCG. First thing I'm going to do is right-click, search for PCG, and grab ourselves a PCG graph. And this is going to be our PCG underscore raycast light. And I know I'm going to need a loop down the line, so I'm just going to duplicate this right away. And I'm going to call it the same thing, underscore point loop. With those two created, I'm going to take our raycast light, I'm going to drag it out into the scene. We now have a volume where our points can all live. With this, we're going to need a spotlight. So I'm going to grab ourselves a spotlight, and this is fine. It doesn't need to be anything special, just a regular spotlight. I'll just place it somewhere around here. And then I'll go ahead and open up our PCG raycast light graph. And with it open, I'll immediately grab our loop and just drag it in and create a loop node. So that way, once we're ready, we can go ahead and start working on this. So one of the first things we're going to need is to get the light, its position, its information, and we're going to need to get the variables that are available to the light. If I have the light selected here in the detail panel, you can see we have access to intensity units, and a bunch of other ones, and we can actually access these within PCG. First, we're going to get actor data. This will get us the light. Now we want to change the get actor data from actor filter from self to all rolled actors. Instead of actor selection by tag, I want to do by class. And the class I want is a spotlight. Now, instead of parse actor components, I'm going to get a single point because I only need the 1 point from this. But now I also want to grab the information, all of the variables from it. Now, how do we do that? We can do that using the get property from object path. Now, this is where you plug in the actual variable. Now, you might be wondering, well, I don't know the variable names. If I want to get, let's say, attenuation radius, what is the actual, name? Well, we can get it by right-clicking and getting internal name. So if you copy internal name here, you can paste that into the property name right over here. Now, it says missing path, but you could take your point and plug it in here. You can do it directly. For that, you can search point to attribute set, and then you can plug this in. But you'll see it complains. It says, hey, we don't have this. This doesn't exist. Well, the thing with this light is, despite all of these variables being available here in the main light, it's actually coming from the spotlight component. If I go ahead and select it, you can see that's where all these values are. So really, we need to get the values from the spotlight component. And so what we can do is here in the property name, we can type in spotlight component dot attenuation radius. And you can see immediately the error has gone away. And now if I press A, and then bottom left, I go ahead and select our light here. You can see we have a double value of value 1000. Now let's go ahead and actually give it an output name. So I'll go ahead and copy this attenuation radius and I paste it as our out attribute name. And you can see we now have the attenuation radius as 1000 all saved here. So just from this, I can go ahead and duplicate it, plug in from the second input. I'm going to grab her outer cone angle. And again, copy internal name. For the output name, I'm going to paste it in here. And I've got the period instead of the attenuation radius. I'm going to put in the outer cone angle. And again, if I press A here, you can see my cone angle is 44, which is exactly the outer cone angle that we have here. So now we can get access to the actual point and its location, everything, and get access to its properties. Fantastic. The next thing we're going to actually need here is how many points do we want to actually scatter in this area? So I could try to find 1 random point, 3, 5, 10, 200 random points within this actual area that you specified. Now, before 5.5, this was kind of a little bit of a pain, but now we have actually pretty much a node that does specifically this. If I right-click and search for point generator, under GPU custom HLSL point generator, we can grab this. And this allows us to specify the amount of points we want. Now, it does need an input. So I'm actually going to take our spotlight and plug this in here. And from our HLSL here in the detail panel, we can specify the point count. And if I press A, you can see we have 256 of 256 points. If I change the point count now to 100, will have exactly 100 points. So no more having to do lots of different math just to generate a bunch of points. You can specify exactly how many points you want here and go ahead and use them. But the point of this is from here, we can go grab ourselves an attribute partition, and we can set this attribute partition to partition based off of index. And now we have all these points partitioned, and so we can now loop this many times. So when you just need to loop on something a certain amount of times, this now gives you a very easy, effectively 3-node system to loop on however many you want. The one downside to this method, though, is there is no outputs here. And there's no inputs outside from the in and out. And there's other ways of getting a points where you can plug in values directly, but if you're not comfortable with typing in HLSL code and your own custom stuff, this is the limitation of this one specific node. In this case, 256 points is going to be fine for us, so I'll go ahead and use it. Next up, we're going to need this loop. So I'll go ahead and double click to open it up. For the input, I'm going to have one input of type point that is set to required, and an input that is a loop of type loop that is also a point that is required. And for the output, we're just outputting the points of pin status normal. That's pretty much all we need here. Now for this, all we need to do is take our attribute partition, plug it into the loop, and get the actor data and plug that into the in. I'm actually going to take all of this, I'm going to cut it, and I'm going to bring it into the loop, because so we don't have it right out here. I can plug it in here, and plug it in to get this information. If I press A and then select our first loop here, you can see attenuation radius is 1000. We have access to the points right in here. So we can get all the variables directly in the loop itself, making it a little more convenient. So how do we now actually get all the points from the light? Well, we can use a new thing called raycasting inside of PCG. Now, raycasting itself is not new in Unreal, but it is new now in PCG, which is awesome. Think of Raycast effectively like line traces. So it's able to line trace in many different directions and get the information you need, and then position points if it hits something of your specific type. So if I right click, get world Raycast, that is our new node. And you can see it takes an origin and a bounding shape here. And says all projected points must be contained within the shape. If this is omitted, then bounds will be taken from the actor, so that points are contained within the actor bounds. So in our case, we're using just a PCG volume. So if we make the volume really small or really large, the points will go ahead and only appear within those parameters if we so wish. You are able to check unbounded for this, in which case it will ignore the bounds. But for our case, we'll keep it bounded. Now, how does this work? We can change the raycast mode. Currently, it's infinite. We can set it to be a scaled vector and normalized with length, and in segments. Now, in our case, I want it to be normalized with length. So every raycast will be a certain length. So I'll set normalized with length, and you can see we get access to the ray length. We can specify the exact value here. So the first thing I want to do is modify this ray length to be our attenuation radius, because that is the length of our light. If I go ahead and open up World Raycast here, there's a ton of stuff here, but really we're looking for ray length right over here. We can plug in attenuation radius right into ray length. And as soon as I do that, if I deselect it and reselect it, you can see it is grayed out because it is now coming from an input here. And to show you what happens already, I'll go ahead and plug this in into the origin because it's going to come from the original point of our light. I'm going to plug the output into the output here. And over here, I'm going to drag out and search for debug, and this will just go ahead and debug it. It's the same thing as pressing D here, but this just gives us a nice little node that we just plug into to see what's going on. You might notice that we don't see anything. Like if I move this around, nothing changes, even though it should be going down. I think, okay, let me clean up and regenerate, nothing. Now, why is this? Well, if I select the actual floor here, in this case, it is set to movable. So it is using a dynamic collision. I'm going to set it to static. Once I do that, if I move my light, you can see we now get a point here on the ground. Now that is fully controlled within the world raycast in our data section. Under filtering here, you can see we're not filtering anything, which is great, where there's no tag filter. We're including landscape hits. But under advanced here, the collision channel was set world static. We were in world dynamic when it was set to movable. So that is why we were not getting any points. Now that we know we're colliding with world static on non-complex, this gets us what we want. We're also able to output information here. Under attributes, we can get impact points, the actual impact, the normal. We can get the distance it traveled. We can get a lot of information. If you just check any of these and press A on the node, select any one of these, all the way on the right, you can see whether or not it impacted, for example. And some cool things you can do is get a reference to the render material, the static mesh, etc. So you can really use Raycast to find out information about things around, not just to create points there. And then you can even filter it based off of the material or the static mesh. So theoretically, you can just have it raycast all around or in a specific area and say, hey, is it passing over the bridge in my level? If it is, then do something. If it isn't, then don't. This really should open up a lot of possibilities for you guys. I'm going to leave all the attributes by default, and we'll just go ahead and use what we have here. So now how do we use this cone angle, and how do we have it actually project all of these points in an area? Because currently it looks like a single point, but realistically it is actually multiple points. One thing to quickly note is you might notice that it's actually a bit of a longer point, and it's not perfectly straight up and down. It's not a square point right in the middle. I'm personally unsure why this is. I have not figured out a way around this. It's not like it's getting the scale information or offset information from the light, so I'm not sure what is causing this. But in general, it'll be just a tiny bit off, and you can offset it yourself. It always will be consistently off, pretty much. So if you want to, you could slightly offset it. In my case, this is fine. This is good enough, so I'm keeping it. But just something you should keep in mind. We don't want to do -1 every time. Well, if we open this up, ray direction is an input. We could plug in a direction here, but we want to randomize it. Randomize it within the angles. So what I'm going to do is take our world raycast and just move it over to the right. Now I want to get a number that's randomized between negative and positive of our cone angle. Well, we have the positive, but we want the negative as well. So I'm going to search for multiply, and I'm going to use a create attribute set to -1 in the detail panel. And now we have the negative value. So now we have negative and positive of the cone angle. And from here, I can search for attribute noise. And if I open it up, we get access to the minimum and the maximum. The minimum will be the one that's multiplied by -1, and the maximum will be our original. So just like so. In the attribute noise, the input source, we're going to change to density, but the output source, we don't want to write it back to density. So I'm going to give it a new attribute name, and this is going to be within angle. And to get our density access, we're going to pipe in from in, plug this in, and now we have a random value. If I press A here on our points and scroll to the right to see within angle, -5.191, because it's positive and negative between the 44 degrees that it was defaulted. But all of these are the same number, and we want it to be actually different for every single point. So we want to vary the seed. So to vary the seed, I'm going to get loop index, and we just plug this in directly. So every loop, it goes ahead and picks a different one. Now this is really nice, but this is only one axis. We want to randomize all 3 axes randomly, so that way it's not always going consistently every single time. So I'm going to take this attribute noise, I'm going to duplicate it twice. The input will always come from the same place, so I'll go ahead and plug it into the same thing for all 3 of these. The minimum and the maximum will also be the same for all of these. So I'll go ahead and plug the same minimum into all 3 and the same maximum into all 3. But the seed we want different. So for the second one, I'm going to get our loop index. I'm just going to add a number here. In this case, I'm going to just add 1 and plug that into the seed. You can add any number, you can offset it with multiplication, division, etc. But this is just a very simple way of doing it. And then for the last one, I'll duplicate it again. And this time I'm going to do 2 and plug that into the seed. And then I'm going to close them up. So effectively, it's going to grab us 3 random values because of the different seed that we're using for all of them. If I press A on the first one and select our first point, we have 30.4, then we have -12, and then -20. And now that we have all 3 of these axes, we're going to use them to offset their current rotation of the point and have it to recalculate the forward direction based on the new rotation of the point. Now we already have access to the point's rotation because that just comes in right with the actor. The first thing we want to do is make rotator from angles. These are angles because we're going off of angles from our outer cone angle. So X is going to go to X, Y is going to Y, and Z is going to Z, basically. These can be plugged in any order at all. These are all randomized within the same range, so it doesn't matter which way you plug these in. But once we have this rotator, we want to combine it with the original rotation of the points. So I'm going to right-click and search for Combine, and you'll see under Metadata, Attribute Rotator Operation, Combine. We want to grab that. We want to combine the actual rotator that we've just created, and we want to combine it with the original point. So I'm going to double-click here to add ourselves a reroute node and plug it in all the way through. Now it's going to give you an error by default, but if you go ahead and select it on input source 1 instead of last, go ahead and change this to rotation. Now this combined rotator, I want to actually output this. So I'm going to call this output target to random offset rotation. If I press A on this and I scroll to the right, we can see random offset rotation roll, pitch, and yaw. And you can see it has now randomized the points. So that's great, but we still need to calculate from the rotation to get the forward vector. Where is it facing based on the actor's rotation? Well, we can actually use a node that we've been using for a while, which is get attribute from point index. The attribute we want to get is our random offset rotation. You plug that into their input source, press enter, and afterwards you can press this plus, add an extractor, rotator, and you want to get the forward. X-axis of the rotation, read only, that's fine, go ahead and grab it. And after I select it and press A, you can see that we now have -1 to 1 directions of all these points, and they're slightly all different. Now, you don't have to have this output target and grab it from the output target. You absolutely can do it from the rotation. If I wanted to, I could just have this go back to the rotation of the point, and here I could specify rotation, and again, get ourselves a rotator forward. It'll get us the same result. If I press A, you can see all the information is still there. But if you plan to add it to an attribute, for example, to keep for later, it'd be good to add the name in. Although, as you can see, it is not required. But now we have this actual direction. So now we can take this world Raycast, open it up one more time, and plug this into the ray direction. So as I do that, you can see, well, we are now getting the actual points in the level. If I move our light around, here it is, it's getting the points. And as I mentioned, it is slightly to the right. You can see it is far more to the right here than it is here. One thing you might notice is it's a little bit of an odd shape. In fact, it's become really square and seems to be going out a little too much. But if I raise it up where it's just barely going inside of it, we pretty much get a perfect circle. And this will be a little more noticeable if I change the attenuation radius to, let's say, 3000. So it's going a little further, but you can see it is now spreading out even further out. But if I have it just within the bounds here, it is pretty much exactly within the bounds. It's only when it goes way too far in that it starts becoming more of a square. Now, that's because we're actually searching for it within all the rotations, and effectively, if you rotate in 2 axes as much as you can, you effectively are making a square. The reason it is a circle here is because it cannot actually make it here because the ray length isn't far enough. But when it's really close, it is far enough, so it is able to get here. So what we want to do effectively is cut off anything outside of the circle. And because the spotlight is effectively a cone, we're going to have it spawn a cone and just say, hey, if it's intersecting with this cone that we're going to have invisible and collisions off, then go ahead and keep those points. Otherwise, remove them. And we'll actually make use of some of the new functionality in 5.5 to achieve this. Now, as always, the project files for this will be available on my Patreon, where you can join these wonderful people here in supporting what I do. It really means a lot. If you'd like to join our community, the link to the Discord will be down below as always. Thank you again to my patrons. Let's get back to it. In our main Raycast light graph, we're going to go ahead and before this debug, we're going to do a little bit of extra. Now at the end of here, what I want to do is spawn a cone to use here. So I'm going to search for static mesh spawner and add ourselves a mesh entry and descriptor static mesh. I'm going to search for cone and grab ourselves a default cone. And the location is going to be our actor data, the original location of the spotlight. And if we come here, you can see we now have a cone. But unfortunately, by default, the cone's rotation and the light's rotation don't match. But that's fine. All we need to do is add ourselves a transform points node right before the static mesh spawner. We can just go ahead and change the Y rotation to +90 for both min and max on Y. And now you can see it is now in the correct area. It is not the correct length or position, though, to match for this light. Now, we will need access to these 2 points of information, the cone angle and the radius. So I'll go ahead and copy these and bring them out here. And then I'll plug it in from the original spot to get access to these values one more time. And then I'll go ahead and open transform points. And on our transform points, I'm going to make sure I don't forget to uncheck uniform scale. Very easy to forget, but we want to make sure that we can make it very tall and without changing the radius of the actual cone. So let's start with actually modifying the scale first. From the scale min, I'll drag out and search for make vector attribute. I'll set it to output type vector 3. And I'll make sure it's plugged into min and max here. Now we want it to be based off the attenuation radius for the height, but we need to consider the height of the actual cone itself. So I'm going to divide this by 100 using a create attribute set to 100 and plug that into scale Z. Now the cone angle, we can go ahead and plug into the X and Y here. If we take a look, you can see we now have our cone, but it is just a little bit offset because the pivot point of the cone, unfortunately, is kind of over here instead of at the very tip. So we need to offset it downwards. So we'll go ahead and grab ourselves another make vector attribute. I'll go ahead and duplicate it for the one up here, and I'll plug it into both offset min and max. And now I want to grab our attenuation radius, and I want to divide it by 2. So I'll grab ourselves a create attribute, and I'll duplicate it over, set to 2, and plug that into X. Now when I do this, you might notice you have a cone, but it doesn't quite match up to the actual light. And why is this? Well, if I go ahead and bring it all the way up, what you'll notice is the actual cone here, right? It cones in, it angles in, but this one is flat. This is a flat shape compared to this one here. So what you can do is go ahead and create a 3D object that is cone shaped and has a spherical bottom, and then make sure it is also 100 units in length. And then you can go ahead and reuse this exact same system, swapping out that one piece, and then it will match pretty much exactly. In my case, I think this is quite fine for what we're doing. So I'll go ahead and just use the cone as it is for now. And as you'll see in a moment, main thing we're doing here is cutting out all the pieces around it. So the fact that it is slightly in is not going to be a big deal. So now that we have this static mesh spawner, it is all working great. I'm going to change some settings onto it. First, I'm going to search for visibility. I'm going to turn visibility off. This makes it invisible in our viewport entirely. I'm also going to search for collision and make sure that it's set to no collision, as I don't want it to affect anything in the world by accident. And now I want to make sure that I keep the points that are overlapping this cone. So from this loop node that we created, I'm going to drag out and grab ourselves an intersection node. And we're going to make sure that it intersects with this point right here. Now, if I did this by default and plugged it into our debug again, and then moved it all the way down, well, you'll notice that we still have all the points going around. Well, why is that? Well, that's because if I select our static mesh spawner, press D to debug it, well, our point is this giant square. Well, because right now, prior to 5.5, you had points that were just points. But now there's new nodes that allow us to get the actual collision information from our meshes, allowing us to use the complex or the simple collisions from our mesh. So before this intersection node, out of the static mesh spawner, I'm going to grab ourselves this new node called create collision data. And if you grab it, it takes in your point information, your mesh information, and you can specify what kind of collision you want. You want simple, complex, simple first, complex first. In our case, I'm going to keep it on simple. I'm going to plug this collision data into source 1 for our intersection. And immediately you could see, here's our points. And it's actually coming within the actual radius pretty much of this piece. So on this debug, I'm going to change the scale method from extents to absolute, and I'm going to change the point scale to 0.3. That way we see slightly smaller points so you can really see where are they actually going outside, and they're occasionally going outside. Now here's something fun. Using this create collision data, instead of simple, what if you selected complex? Well, then you get something quite interesting. Complex collision data effectively is a thin wall. So now you've actually created a donut shape. If I changed our outer cone angle to, let's say, 50, you could see that we now have no points in the middle and points on the outside. So depending on what you're doing, this could become extremely useful to just, instead of having points cut out, if you want a circle of points, this is a way of doing it. And here's the thing. It is actually based off the mesh, which means that if you didn't have a cone, but you had like a star shape and use the complex collision, you could theoretically get a star shape and then have nothing in the middle and just have the points follow the star. Now in my case, I'll go ahead and change it back to simple, as this gets us pretty much exactly what we want. I'll change the debug back to extents so we can see all the points here again. But as you can see, as I go out, the points pretty much stay inside. And if I drag it all the way out, we don't get anything. And because we have this volume and we set it to be bounded, if I place the light in between, it stops at the bounds of this PCG volume. But if I wanted to, in our loop node here, where we have the world raycast, I can check unbounded, and then it extends past this square here. Now, something fun you can do is keep it unbounded with this actual graph. You can just go ahead and move it to the side. It'll generate just a little bit, and then I can copy another one and put it, let's say, over here. And now I've effectively, using one light across multiple graphs here, if I move it in between, you can see we now have a gap in between where they don't connect, but we can go in between the two sections and effectively limit where our light happens. And this is just scratching the surface of raycasting and what is actually possible, but I wanted to get your noggin thinking and of the possibilities that you can now do with raycasting. Just keep in mind, you can combine this with everything else. Combine it with grammar, combine it with dynamic meshes. There's a lot. And we'll continue to experiment and get better with PCG as more and more features get, and as the more experience we gain ourselves. And if you don't know what grammar is, check out this video right here, where I go over one of the best features introduced in 5.5 to PCG.